session now, and today we started already. We're going to work on the board for most of the session. So it is a little bit different than the past two ones. I got a couple of remarks, and let's go over them first. First, I got an email asking, where in the book, in this book, which several of you probably have, where are we in this book? And I think we are in chapter 6C at the moment, and we are going into chapter 6D now. We'll also come back to 6C, so we're not going in the perfect order in that book, but if you want to read up on those parts, it's chapter 6C and D, what we are doing this week, next week, even week up. That about that. The next thing is that another student came to me and pointed out to me that the registrar slipped the discussion registration out of the time which we have over here. So, in particular, some of you registered for a discussion group on Tuesday from 5 to 6, and we don't cover that time. We're going to continue. We have the room anyway from 12 to 6 over there, so it is available for you no matter what. We are trying to be there, covering now from 2 to 3 when some of your discussion groups are, and from 5 to 6 when the other discussion groups are, which means that in the time between 3 and 5, the room might not be covered all the time with the TA. So, of course, I can only ask each of the TA to work 3 hours really there. So we will not be necessarily all the time there. It depends a little bit. Michelle and her would are good people, and if you really need their help, they probably volunteer to do it anyway. But by and large, they might not be there all the time. I'll try to be there on Tuesdays at 1 as well. If I'm not there, several of you found already my office doors to the left of that room. That's where I would be, so get me there. Yesterday we had a very strong discussion group sessions where most of the time Arun was just sitting there and the students were working there, not needing his help really at all except for one note. But other days it's obviously more busy that you need more help. Okay, those two things. Is there anything else that you would like to point out to me? Anybody raising their hand? That's good. Would you want your homework picked up? Let's see that again today, this whole whether we were kind of working or not. Just asking kind of trivial questions here, which you all know from the baking exercise. So let's see that we can get this one here working. See that you can use the whole everywhere feature. I'll give you about a minute or so to do that. And obviously those values aren't super precise. They are rounded, approximate. Really important that you kind of learn what SI units mean in real life. Okay, then I'll start making this active and show the results. And most of you were right, which is very good. It's 28 grams or so for now. well, for having an approximate idea. 30 grams. What's 30 grams? Maybe a mole of nitrogen, 28 grams. A mole of oxygen, 32 grams. The gases, meaning O2 and N2. So, something like that to memory. Ounce, mole of oxygen. Maybe. Okay, let's go to the next one. What tall is he? Okay, so now you have it. And most of you were correct as well. So, maybe 185. Maybe this much shorter than me, so this would be 185. So no, it's not there. 275. No, we wouldn't fit the really anymore. That would be almost 20. So here's not there. Okay, one more, a little bit more tricky. Know them all the time. Every food label has them. You then do that as well. Okay, so most of you, or not most of you, but the strongest group here has the right answer. So what you find here, it's 130 calories, correct? What it says there. Calories is the energy you need to heat up 1 gram of water by 1 degree centigrade or Kelvin. Correct, which is 4.19 joule. So 130 times 4.19, about 500, correct? And then there comes the tricky part. On food labels, the calorie is a kilocalorie, not a calorie really. And so on food labels, it's all in kilocalories, so it's all in kilojoules, and that is why we have to write down. Okay. Thanks so much. Then we had this slide set the last time, and let's just go to that. I have been bothering you with the thermodynamic potential on all those slides all the time. Today we actually are going to be using. So let us first think about the problem which you have for homework, this one. And I asked you in homework, why is that multimeter not showing anything? Why is there voltage in a way between them? Why is there a different electrostatic potential here compared to over here? But why at the same time does the multimeter you apply to there doesn't show you? And there are of course then many right answers to that. And what we looked at over here, just as a reminder, binding energy for electrons in copper is higher than the binding energy for electrons in zinc. That's not astonishing. Copper and zinc are different materials, so one of them needs to have a higher binding energy for electrons than the other. Which one will be the one with the higher binding energy? Of course, the more noble material. Copper is a relatively noble material, zinc is a relatively reactive material. So copper will have higher for electrons. It keeps its electrons back. It's easier to produce. Okay. Now we establish that. So electrons move over from zinc to copper until there is a voltage between the zinc and the copper, which counteracts the movement of the electrons, and they will stay put. Then they will have an equilibrium. Then you will have the vacuum energy and the Fermi energy of the copper raised so much that it corresponds to that of zinc. Or you have lowered the ones of zinc so much that it corresponds to that of copper. You get equilibrium. You get the difference in voltage. Now why doesn't it show anything on the multimeter? Now one way of arguing it is, oh, the multimeter, it's not magically attached to that, it's attached to it via leads, correct? It has some wires. And these are copper wires. So now you're attaching a copper wire here, and you're attaching a copper wire there. And at this point here where you attach the copper wire, you have the same kind of effect that you have over there. And so the multimeter cannot measure any voltage because it is covered by how the lead is attaching to the line. That would be one right answer for this problem why the multimeter can't measure. Because the leads do exactly the same effect, and so the leads on the left and on the right, whatever happens here and there, will cancel each other out. Another way to look at that is to say, okay, this system here, the copper and the zinc attached to each other, they are in equilibrium. They interact with each other. The electrons flow. Once the electrons have established themselves the way they want to establish themselves, the copper-zinc system is in equilibrium over here. The contact potential has formed over there. And if the system is equilibrium, it cannot do any work. It cannot impact in any way anything in the outside world. Particularly, it cannot impact the multimeter over here. You can't do work on the multimeter in order to make the multimeter show you something. And as a consequence, you need to measure zero. It's just as much a correct answer. And in essence, they are really saying the same thing. That if you have an equilibrium establish itself here, then you don't have an effect on the outside world. And the equilibrium can come by having the equilibrium go here and here with the leads, or just internally it doesn't really matter. But there is still a voltage between here and there. Don't get that wrong. There is still a voltage. You just can't measure. Yeah, that's how you can. Right. But not this. So if there's a voltage between them, how big would that voltage be? That might be still something relevant to us. And so let's go back to the formula I keep bothering you with this. U equals the internal energy equals temperature, the price for entropy times entropy, minus pressure, the price for volume times the volume, plus the sum of all the chemical potentials relevant in the system times which are the prices for amount, and then the amounts. This is a good formula over here, but I don't think it's a really good formula yet, because if we have U equals Ts minus PV plus the sum over I mu I and Ni, where do the charged particles are? Where is the charge? Where is the electrostatic component of that? There is no voltage in the whole thing. And so, for the internal energy, I started out asking you in the first session, what is the internal energy of this textbook over here? And then I was suggesting maybe E equals mc squared needs to be part of that as well. The energy of this book based on its mass, like Einstein conversion of energy, mass of each other. And that's certainly not wrong, it's also certainly not very practical either. But the point I'm trying to make is here, whatever the internal energy is of a system depends on what we want to include into that. And that we agree on what we do include and don't include in it. And if we don't agree, it's not a useful measure of internal energy. And that's a big problem with internal energy. So one thing which we can now say we want to include over here is that we have another sum over here, another index which I call I again, but it's not the same I necessarily as on the left. And that is that I'm also summing over all the charges I, Qi in the system, and multiply them with the voltage at the location where that charge is. And in doing so, I'm making two conventions over here. One is that if I'm writing an index in the bottom, I mean that this is whatever I'm numbering over here. Here I'm numbering the different charges, here I'm numbering the different substances with I. And if I'm writing an index in the top over here, then I'm meaning at the location of. The voltage is not a property of the copper. It's the voltage which is present at the location where the copper happens to be. And so there's a little bit of a distinction in that regard. And in order to make the distinction obvious, I'm writing here the voltage when I'm at a certain location. Then the other part which I'm making here is a choice what variable I'll use for voltage. And I chose to use V. There is a real big problem with that. I could use for the voltage U, R equals U over I. You probably have learned Ohm's law in physics at some point. So there people use U for voltage. Problem is if I used U for voltage, I have a U for internal energy here as well. And then I have two U's and they are easy to kind of use. I could use for voltage phi. Many people use phi for voltage. Some sort of Greek letter, capital Greek letter phi. The problem if I use phi for voltage is that I can mix it up right away with the work function, which is also phi. And so I'd rather not do that. Then some books like to use something like an E, very cursive for voltage. My handwriting is bad enough. I don't think you can distinguish between different E's I try to write. So I'm not going to go that way. Also, voltage is really no energy, so I don't really like writing it that way. Then the next way you'll find people write voltage is EMF, standing for electromotive force. I think that is the stupidest way to go at all, because it's not a force, it's a voltage. And so let's not call it a force because it is not a force. And so let's remove that as well. Now, I keep calling the whole thing voltage. You could also call it the electrostatic potential. I like calling it the voltage because that is really what you all learned in some way. If you have an outlet and there comes a voltage out of it, and your batteries, the AA battery has 1.5 volt. So you know all voltage in a way. Even if you look at the light bulb, it says VA, or voltage times amperage, gives you the wattage. So I think voltage is the best way of abbreviating it here. Of course, then there's a problem. There's another V over here. But the way they come in equations, there is barely ever a problem that they are close to each other, and so I think we are fairly safe doing it. So in this class, voltage is V, not U, not E, not EMF, not phi. But in other places, you'll find different letters for that. Okay, good. Now I have a new formula for my internal energy, which is just a little bit expanded about beyond what we had over here. But it's a bit expanded in this peculiar way, where in the sum kind of way. So the charges are always associated with material. There is no charge which is not associated with material. All charges are carried by mass-full objects, electrons, for instance, or ions, or something. So they are actually part of chemistry. So maybe we should not talk about the physics way of talking about charge, but rather we should talk about the chemistry way of talking about charge. Physicists refer charges to the Coulomb, 10 to the 19 electrons, or actually 10 to the 19 protons. Chemists, of course, refer substance to the mole, Avogadro's constant, which is 10 to the 23rd, 6 times 10 to the 23rd objects. So there is a little bit of disconnect between those units, so I can't write here just completely n, I can't replace it just with n, but I can in a way replace it with n, the number of moles of that, and then I'll put a constant called the Faraday constant in there, which is a conversion constant from Coulomb to mole. The Faraday constant is really here just the ratio between Avogadro's constant and how many particles a Coulomb is. And that is on the order of 100,000. That is easy to remember, 100,000. It's not perfect, it's 96,000 something. But think about 100,000, that helps. Okay, and now I then still need to put one more thing in here, and that is the charge number. If I have 2 plus ions, then Z would be 2 plus. I get 2 charges for mole of it. If I'm looking at electrons, Z would be -1 because it's negative. If I'm looking at oxygen molecules, Z would be 0 because they don't have charge. No net charge. Okay. So, and then I still have my voltage in position I. Now if I'm doing this one here, then this sum over here, which is here, now looks very much more like the sum which I have on the left side. So I can actually put them in one sum. So for my internal energy U, I'm getting then Ts minus PV plus sum over I, and then Ni times the chemical potential for substance I plus Zi, the charge number, times the Faraday constant times the voltage where the substance I is. And then I'm having a formula very much like I had it on the board. So we can say that this combination over here of different things, that this combination here, that this is something like a chemical potential again, and I call it mu tilde of I. Now it is not the chemical potential, but it is an electrochemical potential. Electrochemical because it has electrostatic interactions. I could say I have a magnetochemical potential if I have magnetic substances in there, and do the same kind of thing, then the magnetic field and so on would work just the same way. There are many different ways of expanding our chemical potential with external, like how much is the voltage at that location kind of information, and then getting a more complicated chemical potential type of thing, in this case electrochemical potential. So the chemical potential, the price for having a certain substance at the location is the price that it costs, plus the penalty or I need to pay if I have a charged substance in the electrical field, or the attraction the charged substance experiences at that location. I think it even makes sense if you think about it. Anybody not agree? Anybody having a problem here? Okay, that's good. Now, this kind of stuff you had, of course, over and over in your previous class and your thermodynamics class. And a really important part of your thermodynamics class was the stability conditions. So where you then say a chemical reaction is in equilibrium if the stoichiometric coefficient mu times the chemical potential of that substance, if the sum of all of those ones is 0. That was the stability or equilibrium condition. This is one of the key things of thermodynamics. That you can define equilibrium based on chemical potentials in this way. Now if I have an electrochemical system, if I have a system where I have ions and electrons and things like that in there, and not all charges are neutral everywhere, then I need to use my electrochemical potential. Huh? VI? The stoichiometric coefficient, nu I. Thanks for asking, it's always good to ask. Please keep doing it. Oh, and if you ask a question, you feel, oh, that was so bad, I don't want to have it on the recording, you can always ask Haru to cut it out after class. So that's perfectly fine as well. Don't feel kind of hindered by this being recorded and asking a question. Okay, good. Next thing is, now if I have this one, if I have this knowledge, then I can probably go back again and see what we did here. Let's look here again. What do we have here? We have here the transfer of an electron, clearly, from one object to the other. We have here electrons being transferred from the zinc. We have an electron at the location of the zinc, correct? And the electron at the location of the zinc goes to become an electron at the location of the copper block. That is what happened over here, correct? That is how the zinc electron said, oh, I don't want to sit up here in energy, I want to fall down under the voltage drops here to make it less painful. So I have a chemical reaction. That's a nice way of writing a chemical reaction. Only electrons in it, but okay, it's still a chemical reaction. Now, then I have my stoichiometric coefficients over here would be -1 for this electron and would be +1 for that electron. After all, that electron gets used up, the one at zinc, in order to make the electron on the side of the copper. And then I can set up my stability concept, right? So I can then say the sum over I, my nu I times ui tilde equals 0. And this sum, of course, here is just the sum over two things. There are only two sums. There's the electron in the zinc and there's the electron in the copper. So let's first say for the one in the zinc, I have a minus sign for the one in the zinc because it's used up, so the stoichiometric coefficient here is -1, so I have a minus. And then I have here the electrochemical potential, which is the chemical potential for electrons in zinc plus the charge number of an electron, which was -1, times the Faraday constant, which is like 100,000, times the voltage I have at the zinc. And then the sum here, second part in the sum, is the electron in the copper. That has a plus sign because stoichiometric coefficient is +1 over here, times the chemical potential for electrons in the copper, plus still -1 for the electron, times the Faraday constant, times the voltage in the copper. And the whole thing here is 0. Okay? Okay, so I might be interested in asking what's the voltage difference between the left and the right? Even though my multimeter will not measure it, as we said. So, then let's multiply that out first. So, I have a minus and a minus over here, so the whole thing will be plus. So it is a chemical potential, it's minus chemical potential for electrons in zinc, and then minus minus gives a plus, plus the Faraday constant times the voltage in the zinc, and then plus the chemical potential for electrons in the copper, and then minus the Faraday constant times the voltage in the copper. I'm interested in voltage differences, so I need to separate my voltages from them. I need to divide by the Faraday constant, 0 divided by the Faraday constant is 0 still. So is minus the chemical potential for electrons in zinc divided by the Faraday constant plus the chemical potential for electrons in the copper divided by the Faraday constant, and then I have the voltage in the zinc minus the voltage in the copper, which these two here is really the difference in voltage, the only relevant thing. Okay, so if I want to figure out what's the difference in the voltage between those two, then my delta V here is something like minus the chemical potential for electrons in zinc plus the chemical potential for electrons in copper over the Faraday constant. Kind of weird, isn't it? Voltage, like the stuff I'm getting out of the outlet or what I'm getting out of the battery, is chemical potentials. Chemical potentials are molar Gibbs-free function, correct? Gibbs-free energies. So we have here now a direct relationship which brings us the chemical potentials, which we always talked about in chemistry, to the voltages which you might have talked about in the context of physics. They are really closely related. You're raising your hand there?
The delta V equation.
Huh?
Yeah.
That really depends on whether we are looking now difference, which voltage difference we are looking at, right? So yeah, I see why you would say if it's the voltage of the copper over the zinc, that's the wrong way around. If it's the voltage over the zinc over the copper, it's the right way around. Okay? But yeah, good point. Now for the chemical potentials of electrons, what was the chemical potential? What was the price? Was the price and energy I had to pay? Price and energy I had to pay. Okay, correct? Price and energy I had to pay was here, correct? We call that work functions. So really, those chemical potentials here are kind of the work functions. I just need to look up what are the work functions for copper and zinc, and I'll get them. So if I were to look up the work functions, I'll get positive numbers and they need to be negative, and so I have to make that the other way around. The work function would be for copper, it would be on the order of, that's like the key, the work function. Copper is 4.53 electron volt, and the work function for zinc is 3.63 electron volts. I'm not going to go through the problems now, oh, that's per atom and so on. But what you can see over here, I just need to take the difference between these two, right? And then get my signs right. But I just need to look at the difference. And the difference between them is on the order of 0.9 electron volt, correct? One minus the others, give or take 0.9. Now, 0.9 electron volts corresponds then to 0.9 volts difference. That's a nice thing. If I'm doing this with the Faraday constant over here and the Avogadro constant, electron volts, I don't need to think about all of these things. It's just that value in volts. I don't need to worry about that. That's the nice thing about it. Such a can be good. So it's 0.9 volts difference between electrons. The electron part of the volt cancels out the Faraday constant. So, 0.9 volts, is it a lot? Your AA or AAA battery is 1.5 volt, correct? So, almost like battery. Or put it differently, 0.9 electron volt. Electron volt is a unit of energy, so you can convert it in kilojoules per mole, of course. And if you convert it in kilojoules per mole, 1 electron volt is about 100 kilojoules per mole. Combustion of methane, what you use for cooking all the time, I hope, is about 8 electron volts. The combustion energy per mole of methane. So that's 1/8 of that, 1/10, somewhere there. So it's a lot of energy actually, which is involved. It's very similar to, it's a tens. So it's almost on the same scale as the combustion of methane, just the energy which is transferred. So it's a big deal. It's not small in terms of total energies in chemistry. Okay. So, but we are maybe not so much interested in just this one here. So let us do the same thing one more time. Because we like it so much and it is always good. Because now let us look at the Daniel side. Let's take this one. Okay, so let us look at the Daniel side. That's a battery, correct? And for battery, I would like to know what is the voltage between left and right. Now I tell you already, the homework for Wednesday will be to do the same thing for the lithium-ion battery, what I'm doing here right now. So it's of course somewhat different formulas, but not much different formulas. So let me first look at what happens over here at the copper terminal, which is attached to the zinc. Copper terminals. Very complicated way of saying, oh, there's a copper wire attached to the zinc electron. But it's called a copper terminal, technically, so it's a copper terminal. It's a copper wire attached to the zinc electron. What happens over there? Now there happens, of course, the same thing which we just did a moment ago, and hence I said we are going to do the same thing again. So what we have over at that terminal is that we have an electron which is in the zinc can be transferred to an electron which is in the copper. And if we have that, then we can immediately say, oh, stoichiometric coefficient minus 1, stoichiometric coefficient plus 1. We can make the sum over I, nu I, which is 0 at equilibrium, which is this, which is then, as we figured out a moment ago, the negative the chemical potential for electrons in zinc plus F times the voltage in the zinc plus the chemical potential for electrons in copper prime, the copper wire attached to it, the copper terminal, copper terminal here has a small frame up there. Then we also have minus the Faraday constant times the voltage at the copper prime terminal. Okay. But what I really want to know for my battery is what is the voltage which I have here at the terminal, right? If I want to know what my battery is doing, I need to know what is the voltage at the terminal of my battery. So I'm interested in this one. So I use this equation over here to derive myself an equation for what is the voltage at the copper prime terminal. Voltage at the copper prime terminal, that is, if I rearrange the whole thing, is minus the chemical potential for electrons at the zinc electrode, minus chemical potential by zinc electrode over here, plus the chemical potential for electrons at the copper terminal divided by F. Plus, of course, the voltage at the zinc. Okay. Anybody problem with that? Probably not. It's just math. Okay. Then, we can do the next thing. What happens at the electrode? What happens here at the electrode? Oxidation of zinc occurs, correct? So, here at the electrode, I have a reaction for zinc goes into zinc 2 plus, which is in the solution on the left hand side, plus 2 electrons, which are in the zinc. That is the chemical reaction which I have here. Now, if I look at that chemical reaction, the stoichiometric coefficient here is -1. Zinc is being used up. Zinc ions coming existing +1. Stoichiometric coefficient here is 2. 2 electrons are being put into the zinc. Okay? So if I have that, then I can do the same thing which I did a moment ago again. And I will get to so my sum over I mu I equals 0 equals -1 for the zinc over here, which is the chemical potential of zinc in zinc, meaning how much is a zinc atom bound to the zinc electron, right? How much do we need to pay to extract the zinc atom from the zinc electron? Plus the Faraday constant times the charge number of the zinc, which is 0, plus the times the voltage in the zinc. That is 0, okay. So we don't really need to take into account that the zinc atoms are not charged. So no matter what the voltage is, no matter what the Faraday constant is, this component is 0. Plus, now let's look at this one over here. That is stoichiometric coefficient is 1 plus, so we don't need to worry about that. Then chemical potential for zinc 2 plus ions in the solution on the left hand side, correct? And then also plus. Now the charge number for the zinc is 2 plus, so it's 2 times the Faraday constant times the voltage in the solution on the left-hand side. And then finally, I have my electrons over here, and it's plus 2, so it is plus 2 times the chemical potential for electrons in the zinc. That is where they will be at the end, in the zinc electron. And the number is 2 over there, because the stoichiometric coefficient is 2 here. And then 2 times minus 1. Minus 1 is the charge number of the electrons, so minus 2 times the Faraday constant times the voltage which I have in the zinc. That is where the electrons are. Okay, that's really nice, because right now we have a formula here for the voltage in the zinc. Remember what I just erased from the board? There was a voltage for the formula for the voltage at my terminal, which depended on the voltage at the zinc. So now I can actually figure out what my voltage in the zinc is. So let's just rearrange it so that I have a formula for the voltage at the zinc. So my voltage at the zinc then equals minus the chemical potential for zinc 2 plus in the solution on the left hand side, plus the chemical potential for zinc in zinc divided by 2F. And then I also have plus the chemical potentials for electrons in zinc divided by F. And then I also have plus the voltage on the solution on the left-hand side. Just rearrange the top equation. Okay. So I hope you wrote down the previous equation where I'm plugging this one in now. So the previous equation which I had over there, I had this equation that the voltage at the copper 1 prime terminal, that is minus the chemical potential for electrons in the zinc plus the chemical potential for electrons in the copper prime divided by F plus the voltage at the zinc. That is just what I had a moment ago. And now I'll put this one here in, the voltage in the zinc here, that is this one here. So I'm putting it in, so the voltage at the copper prime terminal, that is, okay. This one here survives just the way it is. So let me put this one here in minus the chemical potential for zinc 2 plus ions in the solution on the left-hand side plus the chemical potential for zinc in zinc divided by, I put the minus sign down here, minus 2F. That becomes, if I'm plugging this one in here. And then I have this one here, but that cancels with that. Those two cancel. And then I have left the chemical potential for electrons in the copper prime terminal divided by F. And then I have left the voltage on the left-hand side, in the solution on the left-hand side. So now I have that formula, and now it's time for the class to end. So on Monday we're going to go on from that formula and then divide what is the voltage which we have in that cell. Okay, thanks so much for coming. And you have to do for homework for Wednesday exactly the same thing which I did right now for the lithium-ion battery. If you want, you can get started. Set out those equations which you have access to. And do those Tuesday and Friday. Okay.